66 million years ago, a large rocky object triggered one of the largest mass extinction events in the history of our planet. Near the end of the Mesozoic era, a giant fiery asteroid slammed into the surface of Earth. Approximately 10 kilometers in diameter, this massive object crashed into the shallow waters off the coast of Mexico, striking our planet with an estimated 100 teratons of kinetic energy, equal to about 100 trillion tons of TNT. The immediate blast triggered a swirling firestorm that obliterated entire ecosystems. Radiating from the impact site came a seismic pulse thousands of times more powerful than the strongest earthquake in human history. Gale-force winds whipped up waves more than 100 meters tall. The atmosphere became so clouded by debris that the surface was shrouded in darkness. Causing widespread devastation, the Chicxulub impact event annihilated about 75% of fossil-forming species on Earth, including all non-avian dinosaurs. Nearly all living things on land and sea were affected by this global catastrophe, known today as the Cretaceous-Paleogene or KPG extinction. All those years ago, a 10-kilometer asteroid pushed life on Earth to the brink. But what if Earth was struck by an object 2, 10, or even 20 times larger? Over the last 2 centuries, scientists have identified over 200 asteroids measuring more than 100 kilometers in diameter. Most of these giant asteroids can be found between Mars and Jupiter, where millions of objects orbit inside a torus-shaped region called the main asteroid belt. In the solar system, the main belt contains the largest concentration of asteroids. The largest among them is a giant object named Ceres, which happens to be the first asteroid ever discovered. Ceres is about 950 kilometers in diameter and accounts for more than 30% of the total mass of the main belt. Unlike many of its smaller neighbors, Ceres is roughly spherical in shape with a rocky core and a thick icy mantle. Because of its tremendous size and planet-like structure, Ceres was reclassified in 2006 as a dwarf planet, ceding the title of largest asteroid to a rocky protoplanet named Vesta. Like Ceres, Vesta has a layered structure, but the latter is less spherical in shape. With a diameter of approximately 530 kilometers, Vesta is comparable in volume to another giant asteroid named Pallas. However, Vesta is significantly more massive, representing almost 9% of the total mass of the main belt. Vesta also happens to be the brightest asteroid visible from Earth. In the night sky, it shines so brightly that it's sometimes observable to the naked eye. For now, Vesta's orbit around the Sun is relatively stable, so the likelihood of Earth and Vesta crossing paths anytime soon is effectively zero. Let's imagine that some extraordinary cosmic event knocks this rocky protoplanet out of orbit and onto a collision course with Earth. Currently, Vesta orbits the Sun at an average speed of 19.34 kilometers per second, or 69,624 kilometers per hour. The distance between Vesta and Earth at their closest is about 1.14 astronomical units, or 170 million kilometers, more than 3 times greater than the closest distance between Earth and Mars. Assuming Vesta travels at a consistent rate, it may take several months for this giant asteroid to exit the main belt, soar past the red planet, and collide with Earth. While very unlikely, if such a thing happened, the impact on our planet would be nothing short of catastrophic. As Vesta approaches Earth, it grows larger and brighter in the sky. People across half the world see this incredible sight with their own eyes, at first awestruck and then terrified of this potentially catastrophic event. Emergency alarms sound and panic ensues as billions of people scramble into cars, planes, and safety bunkers. Defenses are rapidly mobilized to protect our planet, but with little time to prepare, a world-ending disaster is all but certain. Roughly 6 hours before impact, Vesta hurtles past the Moon, which orbits Earth at an average distance of 384,000 kilometers. As Vesta draws nearer, it becomes increasingly visible, escalating fear amongst billions of already terrified people. Emergency efforts and evacuations become chaotic, and in many places cease altogether as the asteroid makes its final approach. As it descends, Vesta interacts dramatically with Earth's atmosphere before the inevitable catastrophic collision. An object as massive as Vesta would hit the Earth with enough kinetic energy to transform our planet into an inhospitable wasteland. As rock collides with rock, shards of planet and asteroid explode into the atmosphere, some ejected all the way into space. Rock and debris rain down on the surface as seismic activity fractures the planet's crust. Plumes of molten rock, smoke, and vaporized debris coalesce into thick superheated clouds that envelop the globe, raising temperatures and plunging the surface into darkness. Around the impact site, a crater as deep as the tallest mountains engulfs an area possibly thousands of kilometers wide. Asteroids like Vesta are sometimes called planet killers, not because they physically destroy planets, but because a collision with Earth could eradicate life as we know it. Billions of people, animals, and plants are wiped out in a matter of minutes or hours. Cities are brought to their knees by earthquakes and firestorms. Lush ecosystems where life once thrived are reduced to ash and debris. Marine organisms perish in troves as temperatures soar. Some life forms may survive a day or a week in this world, but eventually all macroscopic life, including humans, becomes extinct. Only the tiniest life forms, like extremophiles, stand any chance of surviving long term. Even for the most tolerant organisms, the odds are slim. The future may seem bleak should a giant asteroid veer toward Earth, but humanity may not be entirely helpless against the whims of the cosmos. Our ability to defend Earth depends largely on how much time we have to prepare. If we can identify a threat years or decades in advance, we can theoretically generate technology capable of destroying or deflecting the object before it enters Earth's atmosphere. In the world today, nuclear explosives are one of our primary weapons against giant Earth-threatening asteroids. According to current simulations, the energy from multiple nuclear explosives, if detonated at a distance, may influence the speed of a giant asteroid. These explosions may slow the object enough to cause a near miss with Earth, thus saving our species from certain demise. There are, however, risks of launching nuclear explosives into space. For one, we run the risk of fragmenting a giant object into many smaller, faster pieces, which are significantly harder to destroy and still capable of devastating our planet. Until recently, our planetary defenses were largely based on predictions and simulations. But in 2022, NASA demonstrated one way to alter a large object's trajectory and potentially avoid a world-ending disaster. Using a technique called kinetic impaction, NASA crashed DART, a high-speed spacecraft, into a moonlet called Dimorphos, which orbits the asteroid Didymos. In a triumphant moment for science, DART struck the moonlet with enough energy to slightly alter its speed, shortening its orbit around Didymos by about 30 minutes. Though only a proof of concept, DART may pave the way for future planetary defenses. However, these technologies only work if we can predict when and where threatening asteroids will appear. Programs like NASA's Planetary Defense Coordination Office, or PDCO, work diligently to locate hazardous objects before they approach Earth. Some near-Earth asteroids, or NEAs, are flagged decades or centuries in advance, but our detection systems are far from perfect. Threatening asteroids have escaped human detection before. In 2013, a fiery object about 19 meters in diameter appeared in the sky over west-central Russia. The object entered Earth's atmosphere largely undetected and soon exploded in a blinding flash about 30 kilometers over the city of Chelyabinsk. Had the object reached the surface, it may have devastated the region and claimed innumerable lives. The Chelyabinsk meteor escaped detection due in large part to the angle of its approach, successfully hiding in the glare of the sun. While this meteor was significantly smaller than a giant asteroid like Vesta, it reinvigorated interest and awareness of potentially hazardous objects in our solar system. Today, space agencies are developing new technologies, like NASA's NEO Surveyor, that can identify a wider range of threats up to a decade in advance. This powerful space telescope will scan the solar system for hazardous objects over 140 meters in diameter, which could cause regional or global destruction. As far as we know, there are no near-Earth objects, and especially no giant asteroids, that pose a real threat to our planet in the next 100 years. Even in 1,000,000 years, the probability of any world-ending impact is exceptionally low. That probability drops even further for giant and relatively stable asteroids like Vesta. By some twist of fate, if this rocky protoplanet veered toward Earth, the stakes would be high. Our species would be in danger, but with enough time and data, we might just save ourselves, our environment, and potentially life as we know it.